Hello, and welcome to Part 3 in the module on patterns and frameworks for synchronous event handling, connection establishment, and service initialization. In previous parts of this module, we first described the reactor and acceptor connector patterns, and then we talked about the way in which the adaptive communication environment, or ACE, implements the reactor pattern in the form of the ACE Reactor framework. And now we're going to talk about how to apply the reactor framework to our JAWS web server. This particular example will be a very simple path through our pattern language. We're going to be using the wrapper facades we talked about before, and we'll be combining it with parts of the reactor framework in order to be able to have a reactive solution. Later, we'll go ahead and generalize this and apply some other patterns to implement other variations in this particular pattern language. Here's a high-level view that illustrates how this particular design is going to work using a reactive approach. What will happen here is that we'll create something called an HTTP event acceptor, which registers itself with the ACE reactor. The flow of control will then be turned over to the ACE reactor, which will wait for clients to send events. When a client connects, that'll cause the reactor to dispatch the handle input method on the HTTP event acceptor, which will act as a factory to create the appropriate HTTP event handler, which will then register itself back with the reactor. That's the connection establishment and service initialization phase. Then, when a client sends over a GET request or some other type of request, the reactor will turn around and dispatch the handle input method on the corresponding HTTP event handler, which will read the request, figure out the corresponding URI that was part of the request message, memory map that, and then transmit that back to the client, and then clean itself up. And these are the basic steps, and you can imagine having multiple different clients connected and these kinds of things taking place concurrently, all driven by callbacks using ACE Reactor. Here's a particular view that illustrates how this works. It's kind of another variant of this particular design. You can see here how we have an ACE Reactor at the core of everything. It's running in one thread of control, and it handles two types of events. It handles accept events, and it also handles data events. So not surprisingly, those are the kinds of things that we'll be using to register with the reactor to tell it to dispatch it when accepts and reads occur. We're going to define two different types of event handlers to make all this work. One of these types of event handlers we've already mentioned, which is the HTTP event handler, and this is the one that's going to process the GET requests. And under the hood, it's going to have an instance of an ACE sock stream that it will use to read the data in and then send the results back to the connected client. We will also have the HTTP event acceptor, and that's a factory that knows how to create the HTTP event handlers. And internal to the factory, it has an instance of the ACE sock acceptor, and it uses the sock acceptor in order to be able to initialize the corresponding ACE sock stream when a connection request comes in. So let's take a little bit of time and look through some of the code here, and we'll show this in a couple different pieces. We'll first start by talking about the HTTP event acceptor, which inherits from ACE event handler in this particular case. So that means it can be registered with a reactor and dispatched by the reactor event loop. We define this factory object called the ACE sock acceptor that knows how to receive accept connections from clients. We use the default reactor singleton, which allows us to have a single place where we drive everything by one reactor in our process that we're using for this. There are ways to override this if you don't like to use singletons. This is a very convenient way to do it. We then have an open hook method, which is going to be used to initialize the sock acceptor to listen on the right port. In this case, we would probably default to port 80, but you could override that if you wanted to. And then it'll also go ahead and register itself. It registers this with the corresponding reactor and says, please call me back when the accept event occurs, when a client connects, when the accept event bubbles up from deep in the bowels of the operating system. I've omitted some of the error checking here just to avoid making the code really convoluted. In real life, of course, it'd be more error checking. Let's take a look at the handle close method. This is the one that's called back when this particular object goes away, say when the reactor is shutting down. In this particular case, it goes ahead and shuts down the acceptor, and then it goes and deletes itself. It's perfectly valid to do delete this in this case, though you have to be careful of this in practice. There's also a method that's called getHandle, and the reactor uses this to do a little bit of double dispatching with the acceptor to get the handle it's going to use to listen on by its synchronous I/O multiplexer. The most interesting method here is the handle input method. This is what gets called back by the reactor automatically when a connection shows up. We'll talk about this method in a second after we talk about the HTTP event handler. Here is the HTTP event handler. This is also an ACE event handler, so it can be dispatched by the reactor framework. As you can see, it has an instance of an ACE sock stream, which will be connected by the acceptor to correspond to the connection with the client. That's in data mode, or the ability to send and receive data on it. It also has an activation method called open, and we'll look and see how that's used by the acceptor in a moment. It's got a little accessor method to give back a reference to the underlying ACE sock stream, and we'll use this in order to access that whenever we need to access the connection to the client once it's connected. There's a handle input method, which will be used when the GET requests or other kinds of HTTP messages show up from clients. And then there's a handle close method that's used when we're going to be shut down, when we're all done processing, or if an error occurs. Now that we understand a little bit about HTTP event handlers, let's talk about how the handle input method of the HTTP event acceptor works. Handle input is called back when a connection arrives from the clients, and as you can see in this particular example, it does several things. It goes ahead and it creates an event handler that knows how to handle HTTP events, GET requests, for example. And then it goes ahead and accepts the connection and stores it into its sock stream. And then it turns around and it says to this newly created event handler, please activate yourself by calling the open hook method. What the open hook method does, as we show here, is this turns around and registers itself, the event handler, back with the same reactor that's being used to drive the acceptor logic. So now both connection accept events and read events, which correspond to GET messages, are going to be handled reactively by the same event loop, object, the reactor. Now, when a GET request shows up from a client, the reactor will call back to the handle input hook method on the HTTP event handler, and that does a couple of things. And notice this logic will start to look very, very familiar because we use it over and over again. What it does is it goes ahead and extracts out the path name from the stream that was passed from the client, so it extracts the GET request and extracts the path name from that. It then goes ahead and memory maps that file, the content that was requested by that path name, and then turns around and sends the result back to the client as a pointer to a contiguous memory object using memory mapped I/O. Now, of course, be aware that a real production web server would do a lot more things than I'm showing you here. I'm just showing you the parts that focus on the networking and concurrency portions. So there's other patterns, other capability that we're not talking about. That would be part of a broader pattern language for a full-featured web server. When we're done, when we're finished sending the file, we go ahead and close things down, and that will cause the stream to be shut down, and we'll end up deleting the HTTP event handler that was allocated dynamically. Note the similarity here between the handle input logic for doing the GET method path name extraction, the memory mapping the file, and the transmitting of that content back to the client with the logic we had had in our earlier wrapper facade-based solution. It's virtually identical. And many of the other solutions are almost identical too. So you kind of get the sense you could reuse a lot of this logic over and over again in different configurations. So let's now go ahead and talk about how we could use the ACE Reactor portion. We talked about how to subclass event handler and be able to have an acceptor and a handler for GET requests for HTTP. Let's now talk about how we could combine all the pieces together with the ACE Reactor class that we talked about before. So keep in mind that the ACE Reactor is going to allow us to run our web server in a single thread of control, but we'll be able to handle connection and GET requests that come in simultaneously from multiple clients, except they'll be handled in a reactive way. To do this, we're going to define a little helper class that we'll use quite a bit throughout the rest of this section. This class is called the Reactor HTTP Server. As you can see, it's got an interesting use of templates and subclassing. It's parameterized by a template, and then that template is then used as a base class for this class. And we're going to actually pass in different kinds of acceptors in this particular example. There's a constructor that we use to pass in argv, argc command line parameters, as well as a pointer to the reactor that's going to be used to run the event loop. Let's take a look at how that constructor would be implemented. As you can see here, we turn around and initialize the underlying acceptor base class, passing in the reactor pointer so it knows who it's associated with, which reactor it belongs to. We then do a little bit of parsing of the argv parameter to get the appropriate port number to listen on. We'll default, of course, to port 80. That's the canonical port number, but you can change that if you want. We then create an address using a trait, so we can write this in a generic way. As long as our acceptor supports a trait called peer adder, then we can pass in many different kinds of acceptors using generic programming. And then we turn around and we say, acceptor, please go ahead and start listening for things to occur. And if something were to go wrong, we tell the reactor, please shut yourself down, we're going to bail out. So that's the basic logic of this little helper class. And we'll use this helper class in other parts of the solutions as well. Here then is the main program. This also will be very common. You'll see things looking like this quite a bit. We go ahead and type def an instantiation of our reactor HTTP server parameterized with the HTTP event acceptor, which we just created. We'll then go ahead and make ourselves the reactor event loop object to control the event loop. We will make a new instance of this type def HTTP server daemon, and we pass a pointer to the reactor into that so it can know how to clean itself up later. And then we turn around and run the reactor event loop. And henceforth, everything else is driven by callbacks using the magic of inversion of control. So you can see that the logic here is very clean, very canonical. As you'll see later, we can generalize this particular approach quite a bit to do other concurrency models, handle other things besides web servers, and so on and so forth. So we've got a very clean starting point for future extensions and evolution of our design. Sometimes it's hard when you look at source code to really see how the various callbacks are taking place and the relationships between the various objects involved in the design. So the next couple of slides, I'm going to kind of walk you through a sequence diagram illustrating how the reactor and the HTTP event acceptor and the HTTP event handler talk to each other in order to carry out the processing logic I just showed you in code. We start out by having the main program register an acceptor who's interested in accept events. We saw that earlier. When a connection arrives, the reactor then calls back through the handle input method on that acceptor, which turns around and creates an event handler. That HTTP event handler then registers itself with the reactor and says, please call me back when read events occur, such as the GET request that comes in from a client. And then finally, when that data shows up, the reactor calls back to that event handler, and it goes ahead and cracks open the message, pulls out the various parts, the path name, memory maps the file, and transmits it back to the client. Very simple example. You'll see later that when we step back and look at this logic, we can actually apply some gang of 4 patterns, such as the template method pattern. And we can use this refactoring in order to help drive the main logic and algorithm of the acceptor connector pattern, which we'll talk about shortly. So to summarize this section, the ACE Reactor version of the web server is much more modular and extensible than the wrapper facade version that we saw before. Even though it does essentially the same thing, it's done in a way that's easier to understand. The wrapper facades help to resolve accidental complexities with programming to low-level IPC mechanisms like sockets, but it doesn't really address architectural considerations. It doesn't really provide you with a framework for being able to extend and enhance and evolve your software in more flexible ways. The Reactor framework, in contrast, provides a nice architectural perspective. That's why it's viewed as an architectural pattern. Its core processing logic, as we saw here, was very similar and very simple, but the way in which we can extend this, as you'll see later, is much more powerful. We'll be able to add lots more capabilities. And most importantly, as we go through many more parts of the pattern language, we'll be able to come up with ways to work around some of the limitations with the Reactor pattern. In particular, its non-preemptibility and non-scalability by coupling it with other patterns to provide much more effective thread pool-based approaches.